Thank you for the introduction. And I would like to express my thanks to the organizers for giving me a chance to talk here at a nice place. And it is very nice to have face-to-face meeting. It's very important. And so today I'm going to talk about a continuum limit of discrete Dirac operator in 2D square lattice. And this talk is based on the joint work with Carl Michael Schmidt at Cardiff. And as my title indicates, my talk is about resolvent convergence. And already Olaf and Christian, they talked about the resolvent convergence yesterday. And so my talk today is somehow related with their talk. So this is my operator, two-dimensional Dirac operator. And so you have already known this operator because Marcus and Christian already introduced this operator yesterday, but let me just repeat it again. And so by dm, I denote this Dirac operator on R2. And here M is supposed to be non-negative. And the sigmas are usual Pauli matrices. And this is my discrete Dirac operator, which is expressed like this way. And this operator acts on the square lattice, and here H is the mesh size. And by this notation, you have D1 sub H, D2 sub H. So these are forward difference operator. And you have D1H star and D2H star. These are backward difference operator. And actually, we have this property. So this star actually means the adjoint of the forward difference operator. And from my point of view, writing like this is much more convenient. And so dm can be written like this, and this m sub h, the discrete Dirac operator, written like this. And the reason is that here we have the Cauchy-Riemann operator. So precisely speaking, so I have to multiply I, then a Cauchy-Riemann operator appears. But in my talk today, it doesn't matter. I call this one a Cauchy-Riemann operator. And here we have the counterpart for the discrete version. And so these two operators plays a very important role later, but let me just move on. And so formally speaking, so convergence of the discrete Dirac operator is quite obvious in this sense. So if you take any smooth function, then the discrete Dirac operator converges to Dirac operator, at least pointwisely. So this is quite obvious. But if we do things from the viewpoint of operator theory, then Dirac operator acts in large L2 space, and discrete Dirac operator acts in small L2 spaces. And so, just in case I am writing down the notation here, so by G sub HD means the lattice, D-dimensional lattice, and by small L2 I mean this one. And so anyway, so what is important is that these two operators act different Hilbert spaces. And so this difference does not make sense. So the problem is that how to embed small L2 into large L2. This is the first problem that I have to think. And this is my embedding. And so for each element in small L2, I assign this step function. Here you have a characteristic function, chi I hn. So here I hn means this cube, or in the two-dimensional case, it's just a square like this. And so for each element in small L2, I assign a step function. So this is important from my point of view because the step function is a discrete object. Then if you take the L2 norm of J sub HF, then you got the volume of this cube, and so we have this equality. And so h to the power minus d over 2 times jh is isometry. So therefore, with this property, I can embed a small L2 into large L2. And if I take the norm, this one, I write down this one. So this is essentially the small L2, but with different norms. And so since JH multiplied by h to the minus to the power minus h half is isometry. So this large L2 over Z sub HD is a closed subspace of large L2. And so naturally we have this orthogonal decomposition. And so naturally we have orthogonal projection of large L2 into this large L2 over Z sub HD. And actually this projection is expressed like this. So actually J sub H phi tilde, and the phi tilde is an element in small L2 given by this formula. And so actually, so P sub H phi is expressed like this with this characteristic function here, chi I H n, for each large L2 over Rd. And we can show that this orthogonal projection PH converges to identity strongly in large L2. And so I want to identify this large L2 over Z sub HD with small L2 with this norm. And moreover, we can define the forward difference operator for the element in this. So we can define the difference operator like this, and also we can define its adjoint by this formula. And so the difference is here. So here we have a characteristic function, and we have summation here. And again, we have this property. And so we can clearly identify small L2 and this large L2 over Z sub HD. And so from now on, I identify each element F in small L2 with element in large L2 over Z sub HD. And the difference operators in small L2 is identified a difference operator in large L2 over Z sub HD. And so as a result, we can regard discrete Dirac operator DMH as the operator in this large L2 over Z sub H2. So from now on, I am working on this Hilbert space, which is a closed subspace of large L2. And so let me come back again to the Dirac operator. So here, the Dirac operator is defined in large L2 over R2, and with domain subspace of order 1. Then it is well known that it is a self-adjoint operator, and it is absolutely continuous. And so it's a spectrum given by the union of these two semi-infinite intervals. So then comes to the discrete Dirac operator. And so this is an operator in the closed subspace of large L2, actually in this subspace. And here, DMH is a bounded self-adjoint operator in this Hilbert space, and it is also absolutely continuous. And so its spectrum is coincide with its absolutely continuous spectrum, and it is a union of these two intervals. And we have h to the power minus 2, and so as h goes to 0, the minimum or the bottom of the spectrum goes to minus infinity. So this means that there is no uniform estimate from below as for this Dirac operator. So in this respect, my talk is different from Olaf's talk. So no uniform estimate from below in terms of h. And so now we have this orthogonal decomposition like this. And so this difference makes sense now. And this is my first result. And so the resolvent of the discrete Dirac operator plus 0h, this converges to the Dirac operator strongly in L2 space. But the difference, the operator norm of difference, its limit if is greater than or equal to this quantity. And so in this sense, so the resolvent cannot converge. So there is no non-resolvent convergence. And so I find this estimate from below is not so bad, because in the general setting, so for any Hilbert space, the self-adjoint operator, its operator norm satisfies this inequality. So this estimate is not so bad. But if you want non-resolvent convergence, then you have to pay the price, because you have to replace this embedding with this one. And this fact was pointed out in the paper by Kornian, Gert, and Jensen a few months ago. And so their embedding is depend on the short function rho. And as a result, this function is now smooth functioned, and so it is not a discrete object. And so, as I said, this embedding depends on the choice of rho. And so, from my point of view, so this embedding looks a bit artificial. But if you want non-resolvent convergence, you have to adopt this embedding. And so let's move on to the proof of theorem 1. First, we need Fourier transform, which is defined as usual. Then we also need discrete Fourier transform, which is defined from large L2 over Z sub HD to here. So dimension can be any number. So I just think in the general dimension. And so discrete Fourier transform L2 Z sub HD to L2 over torus. And here I regard torus just a cube with size 2 pi over h. And the discrete Fourier transform is given by this integral. And here we have a characteristic function. And so these parts are independent of variable x. And so this integral eventually is equal to this one. And this is the usual form of discrete Fourier transform. Then by a Dirac computation, you can show these two formulas. Here for f in large L2 over the lattice. And the inverse of fh, discrete Fourier transform, is given by this one. And so we have the summation here, and we have a characteristic function here. Then this is an element in a large L2 over the lattice. Okay, so let me recall that we have this orthogonal decomposition, and we have orthogonal projection onto this closed subspace. And also, we have these two discrete Fourier transforms. So therefore, it is natural to introduce this orthogonal decomposition and this orthogonal projection. This is just a multiplication operator by a multiplication operator by this characteristic function. So with these projections, I can extend the discrete Fourier transform on all over large L2 like this. So here you have PH, P sub H, then a discrete Fourier transform. Then you multiply this function. Then so this discrete Fourier transform defined on all of large L2. And in a similar manner, I can extend its inverse like this. This is also again defined in all of L2 space. So what is nice is that discrete Fourier transform is defined on all of large L2, and that is the partial isometry, and its initial set is large L2 over the lattice, and its final set is large L2 on the torus. And similarly, we have this property. And also, we have these nice properties. So the product of FH and FH bar is equal to the projection to this subspace, and something like that for the inverse. And also we have these nice properties. And what is nice with this definition of discrete Fourier transform is that we can discuss the strong convergence of discrete Fourier transform in this large L2 space. And also its inverse, we can defined, we can discuss the strong convergence in large L2. So I like this idea. So discrete Fourier transform defined in large L2. Okay. Okay, so with these Fourier transform, I can transform the Dirac operator into a multiplication operator in L2 Xi space. And multiplication is by this 2 by 2 matrix. And similarly, we can transform the discrete Dirac operator plus 0h. So this can be expressed like this. And this part, dmh hat, is also a multiplication operator by this 2 by 2 matrix. And here, 2, 1 component and 1, 2 component come from this formula that we have, I have shown just before. So my proof of the convergence basically use this fact. So for each fixed Xi, dm h hat Xi converges to dm hat Xi. But if you look at the eigenvalues of dm hat Xi and dm h hat Xi, there is something strange. So the eigenvalues of this matrix are given by this formula, and the eigenvalue of this matrix are given by this formula. And here we have a function omega of h Xi. Here, omega of Xi is given by this formula. And since we have the term 1 minus cosine Xi y, and here we have the term 1 minus cosine Xi 2, and so because of these two terms, when Xi is small, the omega Xi behaves like this. And so what we can see is that omega Xi is always non-negative, and its maximum is given by this number, 6 plus 4 times the square root 2. And the important thing is that omega has the value 0 at 2 points. If you think omega on this torus, then at the origin, omega takes value 0, and also at this point, omega takes a value 0. And this point causes difficulties because with alpha at this point, if you plug in h to the minus 1 alpha to here, then you have the square root h minus 2 times mod alpha squared plus m squared. And this term goes to infinity as h tends to 0. But on the other hand, if you plug h to the minus 1 alpha into here, I have h in front of Xi, and so we have omega of alpha here. So even though we have h to the power minus 2, this term vanishes. And so the eigenvalues of lambda sub mh at this point is always takes the value m. This is the cause of the difficulties. But if we look at the value of omega, just a small neighborhood of alpha, then we can write like this. And so again, we have the term 1 minus cosine xi 2 and 1 minus cosine xi 1. So in the small neighborhood alpha, it behaves like this. So using these properties, somehow we can prove this strong convergence in L2 xi. So there is a lot of details between from here to there, but I can't describe every detail just in a few minutes. So I just omit the details. But anyway, we can prove this strong convergence. Then I have to move to L2 X space. Here we have strong convergence in L2 xi space. So in X space and xi space, we have this formula. And so we use this fact, and so we rewrite this term into the following way. And so here we have this one here. And here we have fh minus f and fh bar minus f. But we have already shown that discrete Fourier transform strongly converges to f in L2, and similarly, its inverse strongly converges to the inverse Fourier transform in L2. So in this way, we can reach the conclusion of theorem 1. So this is the rough idea of the proof of theorem 1. Then let's talk about the proof of theorem 2. And the statement of theorem 2 is like this. The operator norm of the difference, its limit if is estimated like this. And so here we have to appeal to the complex analysis. I mean, we need a Cauchy-Riemann operator and discrete Cauchy-Riemann operators. And so what I want to recall is that the famous theorem, Liouville theorem in complex analysis. So if f is a bounded function on R2, which satisfies this Cauchy-Riemann equation, then f must be constant. This is the Liouville theorem. This is just a recall. And then I want to recall a terminology from discrete complex analysis. So monodifferic is just the counterpart of holomorphic function in complex analysis. And so a function on the lattice satisfying discrete Cauchy-Riemann equation is called monodifferic. But there is a big differences. So Liouville theorem does not hold in discrete complex analysis. So which means there is a bounded function on the lattice which is monodifferic but not constant. So a typical example is this function. The right-hand side is it looks independent of h, but this function defined on the lattice z is sub h2, and so we need this subscript h. Okay, so let's get back to the proof. And the basic idea is to construct a family of unit vector which satisfies this inequality. And then, since the norm of u sub h is equal to 1, we get the estimate of the operator norm from below like this. This is because the norm of u sub h is equal to 1. And so we are going to show this part. And actually, we are going to these two terms separately. So this discrete one and this the Dirac operator, we deal with these two terms separately. So I want to give you a formal argument because the rigorous argument, its idea is really simple, just as I'm going to show you. So the formal argument, we just follow the formal argument. But error terms, how to deal with error terms, that is a problem. So anyway, so let me show you the formal argument. So we construct u sub h by this. So the first component is the monodifferent function. Just plain wave. And the second component is just 0. And when we discretize this function, then we get a monodifferent function in the first component. So as I written down, so this is the monodifferent function. And so first, the resolvent of the Dirac operator. So when you go to the Fourier space, then you have plane wave here. So its Fourier transform is a delta function, and which is supported at the point h to the minus 1 alpha. And here you have a multiplication operator. Actually, the resolvent of this is dm hat cosine minus z to the minus 1. And so this symbol, dm hat minus z to the minus 1, it behaves like mod cosine to the power minus 1 as cosine go to 0. And the support goes far away as h tends to 0. And so formally, this term goes to 0 as h tends to 0. Then I come to the discrete part. And so to compute this first, I compute this one, dmh minus z, operated on this vector. And so this is the discrete Dirac operator. And UH, its second component is 0. So we have this vector. And here, W sub h is a monodifferent function. And so this part becomes 0. And so I have this one. And so, and the WH0, this is a vector U sub h. And so from this formula, I get this expression. And then you take the norm of both sides. So the L2 norm of dmh minus z to the minus 1 u sub h is equal to m minus z 1 over mod m minus z times the L2 norm of u sub h. And here I assume the L2 norm of u sub h is equal to 1. This is completely not true. But suppose this one, then we can get this expression. And here you see this in red color. In Japan, when someone say a transparent lie or an obvious lie, we shout, "Your lie is completely red." And so that is why you see this in red here. And so, as I said, we treated these two terms separately, and so we estimate like this, and this second term goes to 0 as h tends to 0, and the first term is equal to 1 over mod m minus d. And so, as I said, this estimate implies this limit if of the operator norm of the difference is greater than or equal to 1 over mod m minus d. So if you want to, but we have to make the argument rigorous, then we replace UH in the previous slide by this one. So here we have Gaussian function. This is our cutting function. And to normalize, we have this constant here. And then everything works. Just we follow the formal argument. But we have to work the error terms. That is the idea. So now I want to mention about assumptions. So here we can allow the perturbation V to be a matrix-valued function, which is assumed to be bounded and uniformly continuous. And so we can allow complex valued potentials. And then this is the Dirac operator, and this is its discrete counterpart. And here, V sub h is defined by this characteristic function. And so this operator is acts in this large L2 over the lattice. And this is our result for the perturbations. So the spectrum of the discrete Dirac operator with potential V is contained in this strip, and similarly, its counterpart, its spectrum is contained in this strip. And here, Vi is the imaginary part of the potential, and imaginary part is defined by this. And here you see B over C2. This is the matrix norm of a matrix, 2 by 2 matrix, as a linear operator in C2. Then for Z, whose imaginary part, its mod is greater than this value, then we can have the similar result as before. And the proof is based on the kind of resolvent equation. So if you write down dm plus v minus z in this form, then this part, dm plus vr minus dm plus vr is again here self-adjoint, because vr is real valued, kind of real valued. And so if the imaginary part of z is greater than this quantity, then this part, its operator norm is less than 1. So you can construct the inverse of this part by Neumann series. And so this means the spectrum of the Dirac operator with potential is included in this strip. And similarly, similar statement holds for the discrete Dirac operator with potential. And to prove the resolvent convergence, we use the resolvent equation. And this resolvent equation holds in this closed subspace, large L2 over the lattice. then we have already shown that without potentials, so we have this strong convergence result. And so as a result, we get this convergence. And this one is exactly the resolvent of Dirac operator with potential V. And so this is the idea or my proof of theorem 3. And so thank you so much. Okay.